right, I want you to picture this. You're out in the pitch-black waters of the North Sea. There's a storm raging that's literally strong enough to capsize a supply boat. The waves are absolutely massive, the wind is howling, but the driller standing on the floor of a towering offshore structure, they don't feel a thing. No swaying, no rolling, just perfect stillness. Now, that's not some crazy fluke of nature. That is extreme engineering doing exactly what it was designed to. Welcome to this explainer on the Gusto MSC CJ70 design, better known as the Equinor Cat J class. Today, we're going to unpack the biggest, harshest environment jackup drilling rig ever built. To really wrap your head around the scale we're dealing with here, just look at this number, 69. That is the rig's operational air gap in meters. When this rig jacks itself up out of the water, its massive steel hull sits 69 meters, or over 220 feet above sea level. You might be wondering, why on earth does it need to be so high? Well, that massive clearance is a vital safety buffer. It keeps the bottom of the hull safely above the absolute highest crests of a 100-year North Sea storm wave. Okay, let's dive into this. We're going to do a bottom-to-top climb of the rig. We'll start with the foundation, move up to climbing in power, check out the drilling muscle, explore the digital brain, and finally, look at the well barriers. So kicking things off with Section 1, the foundation. We're talking hull, legs, and the seabed. Every jackup basically lives two completely different lives, right? First, it's a boat being towed to a location, and then it transforms into a fixed platform on stilts. At the heart of the Cat J is this watertight steel hull measuring 297 by 378 feet, and it's supported by three massive, roughly 700-foot triangulated lattice legs. These legs are incredible. They convert the intense bending forces from ocean waves into simple tension and compression, giving the rig immense structural strength. When you compare this to a standard rig, the leap in capability is staggering. While a conventional rig might tap out in shallower waters, the Cat J boasts a 150-meter water depth capacity and a maximum drilling depth of 10,000 meters. That means operators can actually reach the deepest, most complex, high-pressure reservoirs on the Norwegian continental shelf. But how does a structure this insanely heavy stand on the ocean floor without just sinking straight into the mud? The answer is sitting at the absolute bottom of those 700-foot legs. They're called spud cans. These are massive, skirted footings that interact directly with the hazardous seabed. They dig in and lock the rig firmly in place, which keeps it from sliding laterally, even if it's sitting on sloped underwater terrain. Think of it exactly like walking in deep snow. If you step in regular boots, you're going to sink straight down. But if you strap on snowshoes, you spread your weight over a much larger area and you stay on top. The spud cans use this exact same snowshoe effect, and this design is absolutely critical for preventing something called a punch-through. That's a catastrophic event where a leg suddenly breaks through a hard crust on the seabed and plunges into a soft layer of clay below. To prevent that fatal drop, crews do an incremental preloading sequence, basically gradually applying weight while the spud cans safely distribute all that force. Moving on to Section 2, climbing and power, surviving the ascent. So, the rig is securely planted on the seabed. Now, how does it actually get out of the water? It is honestly mind-blowing that thousands of tons of steel can lift themselves entirely out of the ocean without using a single hydraulic ram. Instead, the rig uses independent electric pinion gears powered by variable speed drives, or VSDs. These gears physically climb up toothed steel racks running up the leg cords. Because each gear operates independently, the system is auto-leveling the massive hull in real time. But this introduces a highly critical safety metric called rack phase difference, or RPD. This measures the difference in the vertical position between adjacent jacking units on the exact same leg. And this brilliantly illustrates why RPD is so important. Imagine you're lifting a heavy timber house using a jack at each of the four corners. If one jack pushes up faster than the rest, the whole frame is going to twist and crack. It's the exact same physics here. An RPD alarm means uneven load distribution, and for the crew, that is an absolute hard stop to prevent catastrophic twisting of the legs. Once the rig safely reaches its final drilling height, heavy-duty counterracks click into place. That takes the load completely off the gears and locks those legs totally rigid. Naturally, to run all these jacking motors and massive drilling systems, the rig needs a colossal amount of power. The standard Cat J configuration features dual engine rooms housing four 2,500 kilowatt and two 1,750 kilowatt diesel generators. Splitting them into two rooms is super smart. It ensures that a fire or a failure in one room doesn't knock out the rig's power. But recently, a sister rig in this class named the Askapot got a major game-changing upgrade in Q4 of 2024. They electrified it. It now plugs directly into the shore grid via a high-voltage cable from the nearby Martin Linge A platform. That upgrade wipes out an incredible 20,000 tons of CO2 emissions annually by silencing those massive diesel engines. But, and this is a really vital detail, those diesel generators didn't actually leave the rig. They are still sitting on board as a critical redundant backup. Because offshore, you never, ever trade redundancy for efficiency. You just shift your primary source. All right, Section 3, the drilling muscle. Let's look at top drives and cantilevers. Now that we've got our solid, powered platform sitting safely 69 meters in the air, let's head up to the real powerhouse of the entire operation, the drill floor. This is where the Cat J goes from being a marine vessel to a total industrial titan. Just look at these massive specs. You've got a bolted H-profile derrick towering overhead that can hoist 2,140 kips. Guys, that's over 2 million pounds. Right under it, a 5,750 horsepower NOV drawworks handles the heavy lifting, while an NOV top drive blasts over 92,000 foot-pounds of rotational torque down into the drill string. So the absolutely crucial point here is that before they do any heavy casing run, the crew must verify that the derrick's hook load limit easily exceeds the total expected weight of the string. The math has to be perfect, every single time. But Gusto MSC engineered a pretty incredible innovation right beneath all this heavy machinery, the XY cantilever. On older rigs, if you needed to drill a cluster of wells, you often had to pack up and move the entire rig. The XY cantilever is this genius skidding system that lets the entire drill floor package slide outward, over the edge of the hull, right over open water. And it can move seamlessly forwards, backwards, and side to side. The craziest part? It manages all these movements while keeping live, high-pressure mud and hydraulic lines fully connected. Think of it exactly like the print head on an old dot matrix printer. That head slides on two axes, left, right, forward, back, to put ink anywhere on the page without you ever having to shift the paper itself. The XY cantilever does the exact same thing over a multi-well template on the ocean floor. It saves a ridiculous amount of time and massively reduces operational risk, all because you don't have to constantly jack down and relocate the entire rig. Moving into Section 4, the digital brain. Let's talk about the human-machine paradox. Stepping away from the roaring noise of the drill floor, we enter a remarkably quiet space. We're trading raw physical muscle for the highly advanced digital network that actually runs it. Inside the driller's cabin, you are not going to find old-school brake handles anymore. Instead, you'll see the NOV cyber-based dual-chair console. It's basically this wraparound cockpit of screens and joysticks. From here, the driller runs the Navo's Automated Drilling Control, or ADC. This software can automatically adjust the weight on bit and rotational speed. But the real secret sauce making this real-time, closed-loop automation possible? It's wired drill pipe telemetry. Instead of relying on really slow mud pulses to send data to the surface, the drill pipe itself actually contains high-bandwidth wiring. It sends incredibly rich data from thousands of meters downhole straight to the software in an instant. Now, what's really interesting about this slide is it brings up a surprisingly deep question. Does more automation always mean more safety? I think we naturally assume that putting a smart computer in charge of routine tasks eliminates human error. But offshore, the reality is quite a bit more complicated. A regulatory audit by Havtil, the Norwegian Ocean Industry Authority, actually flagged a fascinating human factors risk with this exact system. They warned about something called alarm fatigue. Imagine a wall of blinking lights constantly competing for the driller's attention. More importantly, they warned about the danger of the driller losing their manual feel for the well. If the computer is making every routine micro-adjustment, the driller might miss really subtle physical cues, like a gradual increase in torque that means the hole isn't cleaning properly. It's kind of like a distracted driver using adaptive cruise control on the highway. The system works beautifully right up until a sudden edge case requires an instant human reaction. So the big takeaway here? Automation should absolutely reduce workload, but it can never, ever be allowed to reduce situational awareness. And that brings us to Section 5, the well barriers, holding back the pressure. We've talked about the immense power and the digital brains, but what actually happens when the Earth pushes back? Well, before we look down the well, we have to look after the 120 to 140 people living on board. Their accommodation block wraps safely around the forward leg, keeping them as far from the drill floor as possible. But if the absolute worst-case scenario happens and they need to abandon the rig, they rely on a record-breaking Viking 81-meter evacuation chute. Because obviously dropping straight down 26 stories would be fatal, this Kevlar and Nomex chute is designed in a tight zigzag pattern. It intentionally bleeds off a person's speed at every single turn, almost exactly like a high-rise fire escape, ensuring they safely splash down into a life raft below. Let's move on and see how this builds into the ultimate progressive safety net for the well itself. It all happens in 3 really deliberate stages. First up is the mud column. Driven by 3 huge 2,200 horsepower pumps and cleaned by a progressive solids control system, this heavy drimming mud provides the primary hydrostatic barrier against the raw pressure of the reservoir. But if that mud balance fails, we immediately hit step 2, the surface blowout preventer, or BOP. Sitting right under the rig deck, this massive mechanical valve is rated to hold back a staggering 15,000 psi of pressure, which buys the crew precious time to regain control. Finally, step 3 is cement. It's pumped down to permanently seal the well and provide permanent zonal isolation once all the drilling is done. And that really brings everything full circle, doesn't it? The Gusto MSC's CJ70 Cat J rig is just an absolute marvel of scale, redundant safety, and raw power. From those 700-foot lattice legs resisting brutal North Sea storms to the newly electrified power plants to the ultra-fast automated drilling controls, it really forces us to ask a big question. When extreme human engineering meets the harshest forces of nature, what is the next generation of offshore safety going to look like? Because even as we rely more and more on digital brains and heavy automation to push boundaries further and deeper than ever before, at the end of the day, it's still the human sitting in that chair who has to master the machine.